16, is it 16b? Yeah, 16b. Last slide of 16b. And there is this question. Remember, the Michael addition is what? It's the addition, you're forming a 1,5 diketone. So revise this. The question that's on the slide is the following. Okay, we have a ketone here, CH3, H, we have a double bond, plus, okay, in the presence of KOH and methanol. This is the setup for the Michael addition. Okay, you're asked to produce the final, you're asked to provide the mechanism for the final product, and the final product looks like this. This is a CH3. I have a double bond there. Let me fix that. And then we have this. We're trying to find, let's go ahead and label our 1,5 diketone. 2, 3, 4, 5. 1, 2, 3, 4, 5. So 1,5 diketone. This was a question that came in our exam. It wasn't as straightforward as this, but it involved the ring closure. So if you look at the mechanism, there is this is the slide after. So this is the one before the last practice question. Yeah, you end up closing the ring, and then you eliminate H2O and you form this double bond here. So that was 2 questions. It was on the last page of our exam. It was like this 20-step question. Not to be scary or anything. The reagents were all given, but you were asked to basically supply the final product. And the last step, I remember this, was this here. I think he even changed the reagents, and he only gave us OH minus and heat. But that's the thing that confused me. The fact that there was heat there, I was a bit confused. I could be wrong. So take this with a grain of salt. But the OH minus heat was meant to sort of give you a hint that you're forming this double bond here in that last step. Okay? I know I rambled for a bit. Let me know if I lost you guys. Any other questions? I like the Michael addition. It's a nice reaction. Anyone else? Go ahead. Ask away. Is there a slide that doesn't make sense, a reaction that's confusing? Or if you want me to give you a practice question off the top of my head. In chapter 16b, slide 40, can we use the Wolff-Kishner instead of cyclic thioacetal? Slide 40. Which, are you talking about the last question? The one where it says carry out the following transformation? Yes, okay. Which step are we looking at? We're looking at, the last step where you use BF3 thioacetal. Could you have used, the question is, could you have used Wolff-Kishner? Remind me, what is the Wolff-Kishner reaction? Give me a second. Yeah, you could have used the Wolff-Kishner. Yeah. And what's the point of Raney nickel? Okay. So yeah, you could have used Wolff-Kishner in that last step instead of the thioacetal. You're asking what is the point of Raney nickel? What's the point of Raney nickel in general, or what's the point of Raney nickel in this question? You know what? I'll answer both. Raney nickel is just a special preparation of a nickel catalyst for hydrogenation. When we use it with BF3 and thioacetal, let me erase this. Okay, so just R. Let's just take our ketone over here. Ketone, double bond. Whenever we react it in the presence of this BF3, we form this thioacetal protecting group. Remember? S. To remove this group, we said we did what? We're going to add H2O, H3O plus. Remember? H2O, H3O plus. Acidic workup. Great. But what if I wanted to completely reduce this ketone? Meaning I wanted to replace it with hydrogens. So hydrogens. How the hell would I do it? There's so many ways that you've looked at in this chapter or in the whole course. One of them was using zinc, mercury, and then you reflux, right? Another one is this, where you just take this extra step. Where you take this extra step and you add Raney nickel and H2O. And H2, hydrogen. Okay? It's just a way of reducing this ketone to your alkane in this case. Okay? Why do we have to go through this? Because sometimes, as you've seen in some of the practice questions you've probably solved, you want to replace, maybe this group isn't an R. Maybe this group isn't necessarily an R and it's a hydrogen. And by adding this, forming this thioacetal protecting group, you can replace this hydrogen with some other R group, right? And when you replace with an R group, you have so many different reactions that you can proceed with. And then maybe you want to get rid of this ketone, okay, or this carbonyl group. So that's why we use Raney nickel, okay? I hope that answered your question, Rio. We have to memorize the groups that are activating and deactivating. Yeah, you do have to be familiar. You absolutely have to be familiar with the activating, deactivating groups. Are they ortho, para, meta-directing groups or meta-directing groups, however you want to pronounce it? You do need to be familiar with those. And I'm not sure if he said he's going to give you those on like the formula sheet or whatever it is. So you'd have to double check with the professor. I have a question. Okay. How do we solve retrosynthetic analysis and the synthesis of any transformation? Like, could you give us tips or hints? Of course, I love retrosynthetic analysis and synthesis. Some general tips. Typically, whenever it comes to synthesis and retrosynthesis, pro tip, always just look at what you're starting with, okay? What am I starting with? Am I given any constraints? Because sometimes you might get questions where it's like, use only reagents of 3 carbons. That's a limitation. Or use this. So identify if there are any limitations imposed on you, if the question limits you to a certain set of reactions. Then look at your compound and identify what is changing on the start versus the end. Once you identify all the groups that are changing, you now have done what? You've narrowed the problem solving from every possible reaction that we have ever looked at to, okay, I'm changing this carboxylic acid to an amide. Okay, so now we're looking at all reactions involving carboxylic acids and how the hell do we get to an amide? So on and so forth. So biggest tip, start off by identifying constraints, limitations. Second one is now what the hell is changing on my starting compound? What's on my final compound? There's nothing on the board, by the way, so you guys aren't hallucinating. What is on my starting compound that's changing on my final compound? Identify what potential reaction or reactions, because you might have a structure, and then you're going to need 3 or 4 steps to get to that final structure. How am I going to know the 3 or 4 steps in the middle? Practice, number 1. And 2, trial and error. A lot of this is trial and error, guys. This isn't math. This isn't physics. There's no formula that we can use that'll absolutely every single time give me, the final answer, right? And as a proof of concept, let me I'm going to ask you guys, if you have a specific question about retrosynthesis or the synthesis or synthesis and any transformation question, go ahead and ask me. If not, I can think of one question that I gave to someone a couple days ago that we can practice together, and I can show you how to approach solving some of these questions. So, Aya, if you have any questions. Yeah, okay, so let's go ahead and do one. Where can you guys stop seeing the camera? Because I need to first practice. Okay, you guys can't see this. So I'm just going to quickly write something here. I want to see if I got it right before I do anything. I know that's wrong. Give me a second. Okay, don't worry. You guys are going to be able to solve this one. It's not difficult. Not the end of the world. Where's my phone? There it is. Okay. Okay. We end up with the following. Just a second. I forgot how a structure looked like, guys. Give me a minute. Okay, got it. Thank God. Okay, all right. I know that was a really long pause. Sorry, guys. We got it. Okay. So synthesize the following compound. I'm smiling because I feel like this is too mean. But this is the exam. Or is it? Okay. Prepare the following compound using Okay, yes, go ahead. Any brave soul, please go ahead and unmute. Prepare the following compound. So, anyone want to give it a shot? Come on, people, come on. This is exam practice. Don't be afraid. Okay, let's get started then. Step one, what's the major limitation? Well, the major limitation is that I got to start with this weird compound, and I need to somehow make it into a ring, okay? Rings are scary because people are like, what? A ring? Not that scary. Step one, identify what the hell is this compound? Okay, what do I see here? I see that this is a carboxylic acid. Great. I see that I have some sort of chlorine here at the end. Okay, some sort of a halogen. Okay. I'm forming, what group is this? Any guesses? Can anyone guess what this is? The name of the compound, not the name, but the just group. Don't afraid from cyclic. Okay. Number first. Okay. We have ester, close. Okay. It is a type of ester. Yes, you're correct. Heat is there. Okay. Okay. A lot of good responses. So let's collect everything we have. So we said that this group here. Let's try to figure what this group out. Try to figure out what group this is. We are ester. I'll help you out. Specifically, this is a delta lactone. This is a delta lactone. Delta lactone. The reason I asked you to start with this is because the second you figure out what this is, what functional group it is, it will immediately inform your ability or inform your decision making on how the hell we make delta lactones. Delta lactones are made from what? That's the next thing I want to. This is how you should think of these, right? It's you're trying to pick clues from everywhere. Like try to find as many clues as possible, and then that'll inform what steps you take to get here. So we've identified this information here, not as important. Biggest piece of information is that this is a delta lactone. Great. How the hell do we make delta lactones? How do we make delta lactones? Carbo and ketone. I don't fully understand what you mean by that. Explain. Delta lactone. Made by maybe a carboxylic acid and ketone. Okay. So it is definitely a carboxylic acid. So you got that part right. And where do we have a carboxylic acid? Well, right here. Perfect. Okay. Delta lactones, let's move one step back. Delta lactones are made from delta hydroxy acids. Delta hydroxy acid. This is how we can go from this is how to produce a delta lactone. So delta hydroxy acids will give us delta lactones. Great. What the hell is a delta hydroxy acid? First off, ask yourself, what the hell, what does, I keep saying hell, sorry guys. What does delta signify? Delta signifies just our own sort of way of identifying the carbon atoms. Carbon atoms relative to what? The carboxylic acid. Because delta hydroxy acid, we're going to start with this carboxylic acid, and let's go ahead and give it these Greek letters. Alpha, beta, gamma. What's gamma again? I think gamma is like this. Alpha, beta, gamma. Wait, alpha, beta, gamma. I forgot. What are the Greek? What's the Greek alphabet again? Alpha. What were the Greek letters again? Sorry, guys. Alpha something. Oh, yes, I got it correct. Sorry. Alpha, beta, gamma, delta. Yes, you're right. Sorry. We start from here. So this carbon is alpha. This carbon is beta. This is gamma. And then this is delta. Okay. This is delta. So our delta, we're talking delta hydroxy acid, which means that on our delta carbon, we should have what? A hydroxy, which is just an OH group. Okay? And acid here means carboxylic acid. Carboxylic acid. So R double bond O, OH. Great. We have this carboxylic acid attached to the alpha carbon, correct? Great. Can everyone see so far? Just want to make sure everybody can see. Yes, great. Okay. We have our alpha, we have our beta, we have our gamma, we have delta. We want to have a delta hydroxy acid. Do we have a delta hydroxy acid here? No, we have a delta halogen. We have a halogen here. So the first thing we want to do is replace this halogen with an OH. How do we do that? Remember from organic 1? What can we use? We can use a nucleophile. What's a good nucleophile? OH minus. From NaOH, for example. This will come in, boom, replace the Cl, kick the Cl out. Okay? So we redraw everything exactly as is. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Great. Except now we've replaced it with an OH. Well, now we officially have our delta hydroxy acid. Delta hydroxyl group acid. Perfect. Everything clear so far? Have I lost anyone? If I did something that made no sense, let me know. Okay, good, good. I'm going to move the camera a little bit to make some space. Move the camera a little bit. Okay. So we're here right now. We officially have our delta hydroxy acid. The next thing is, what are the steps that are going to take me from this to this? Someone correctly answered. Someone said, we're going to need to add an alcohol. Okay, almost there. Wait. With this delta hydroxy acid, we know that all we need to give it is what? This is in chapter 16a, I think. All we need to do is have this react in the presence of H3O+, or some weak acid HA. HA if you want. And then what's going to happen is the following. You're going to have this intramolecular cyclization. I'm going to erase this for a minute, guys, so I make some space. You're going to have the lone pairs on the hydroxyl group come in and attack the carbonyl here. You're going to attack the carbonyl. Once that happens, you're going to break these pi electrons and electron density collapses towards oxygen. This is the thing that confuses people. How the hell do I number? Well, you always start numbering from the thing that's attacking whenever you're forming a ring. Always start numbering from the thing that is attacking to the last carbon atom or the last atom that it touches. So let's do this in a different color, green. This is number 1. This is number 2. This is 3. This is 4. This is 5. This is 6. The last group those lone pairs go to. So we know we're forming what? A 6-membered ring, which is our final product, which is the delta. Oh, you can't see that. It's the delta lactone, essentially. So let's, step 1, draw a 6-membered ring. A 6-membered ring. We've seen these before. Great. Now let's go ahead and start assigning numbers. Pick a direction. Clockwise, counterclockwise, whatever you want. I'm going to go clockwise. 1, 2, 3, 4, 5, 6. Now all you have to do is match up the numbers you have assigned here with these numbers. On carbon 1, on position 1, what do we have? We have an O. Okay, great. Let me go ahead and erase this, replace it with an O. It is attached to a hydrogen. Perfect. There are 3 bonds on this oxygen, right? This is the number 1. I should make that a bit clearer. There are 3 bonds on this oxygen. When oxygen has 3 bonds, it has a charge of plus. Great. Move. Carbon number 2. What do we have attached to it? We have this methyl group. CH3. Great. Carbon 3, 4, 5, nothing. 3, 4, 5, nothing. On 6, what do we have? We have our OH group. OH. We also have this single bond now. O minus. O minus, because we broke those double bonds. Remember? Okay. Now what are we going to do? Now, this is where H3O plus comes in. We're going to protonate. This O minus will come in and attack the H3O plus. You're going to lose one of those hydrogens, you form H2O. Great. Let's go ahead and draw. Am I running out of space? No, I shouldn't. Okay. Draw everything as we see it. We're going to have our CH3 up here. We're going to have our H plus 2, 3, 4, 5, 6. We have now 2 OHs. OH. And remember, these guys have lone pairs. This will be important in just a second. Okay, great. Now, what's the next thing we want to do? The next thing, we want to get rid of this H up here. Well, what in this system right here could potentially get rid of this H? Well, look right next to it. You have 2 OH groups with lone pairs. Pick one. One of these is going to come in and deprotonate this O right here. Electrons are going to collapse towards this oxygen. Drawing everything again. Do I have space? I do have space. Okay. Actually, I'll just draw up here. Putting everything together, we have the following. O. We just removed the hydrogen from here. CH3. Nothing down here. Nothing down here. OH. O. H. We just protonated this OH group. So we're going to have OH2 plus. Okay, we're starting to see resemblance with our product. How are we going to kick out this OH2 plus group? Very simple. Let me actually make this a little bit more clear to see. We have our OH2 plus, and we have our OH group. This OH group is going to donate electrons to kick out this OH2 group. Why? Well, because carbon can only accommodate 4 bonds. 5, something has to break. That's going to be this OH2 group because it's already it's about ready to leave, right? It's very electrophilic. I think we have space. You guys can see up here. Good, good. We're going to build this double bond. So let's go ahead and undraw our O here. We have a CH3. And we just did what? We built a double bond here, but we also have H attached to it. 3 bonds on oxygen plus. Great. Now we need to get rid of this H. How are we going to get rid of it? Well, there's got to be something in solution that has lone pairs. Well, we just kicked out OH2 plus. When we kick out OH2 plus, we form H2O. H2O will come in and remove this hydrogen, deprotonate the carbonyl. Electrons collapse here, and you end up with the following final structure. You guys can still see? Great. O, CH3, double bond, O. And this is our delta lactone. Let me go ahead and move the camera so you can actually confirm. Boom. This is the same as this. Don't believe me? Carbonyl, carbonyl. O, O, CH3, CH3. Nothing here, nothing there. Only thing is that the orientation looks a little different. Makes sense? Do you guys understand how I approached this? It seemed long, but that's because I was going step by step. I was thinking out loud, making sure that I understood what was going on. I numbered things. When you're in the exam, you don't have to move this slowly. You can be very quick with it, but make sure before you proceed with any reaction, any synthesis, you establish all of your knowns, all of your unknowns. What are my limitations? What groups are changing and what? How can I change those groups? Narrow things down until you have a clear line of focus. What am I dealing with? What are the potential reactions? Okay? Oof, I feel like I sped through it. I'm sorry, guys. Let me see. Yeah, let me go ahead and zoom out for you guys. Okay. Feel free to screenshot it, take a photo. Okay. Any other questions? Or do you guys want to do another practice problem? What about chapter 12, slide 46? I hope the slide isn't messed up on your part. Bromobenzene to benzyl alcohol. Yeah, I remember this question. I think we